The night sky looks finished. The stars are set, the galaxies hang quietly where they have always hung, and nothing about it suggests a beginning. Then the James Webb Space Telescope stared at a patch of darkness, roughly the size of a grain of sand held at arm's length, and found something there. Its name is JADES-GS-z 14-0. Its light left when the universe was about 290 million years old, which is around 2% of the age it is now. The galaxy is more than 1,600 light-years across, and it was already blazing with young stars. That is far too much, far too soon, and the astronomers who found it said so. Tonight we go slowly out to the edge of time, and we look carefully at what Webb saw waiting there. Somewhere in the constellation Fornax, in a stretch of sky that looks empty through any ordinary telescope, there is a patch of darkness that astronomers have stared at for years. It sits inside a region called the Good South Field, chosen decades ago precisely because it seemed to contain nothing. No bright stars to flare across the detector, no dust from our own galaxy to fog the view, just a clean window onto the deep. The James Webb Space Telescope pointed at that window and opened its shutter for a very long time. What came back was an image crowded with galaxies, thousands of them, layered over one another like leaves at the bottom of a pond. Most are ordinary, spirals seen from strange angles, ellipticals gone orange with age, smeared little clumps that were probably in the middle of a collision when the light left them. And then, near the middle of that image, there is a smudge. It is faint. It is red. It is small enough that if you were shown the picture without help, your eye would slide past it 100 times. It has a catalogue name, JADES-GS-z 14-0, which tells you almost nothing except that a survey found it and gave it a number. Here is what is strange about it. When astronomers looked at that same position through Webb's shorter wavelength filters, the ones tuned to light that our eyes would call blue and green, the smudge was gone. Completely gone. Nothing there. Only in the reddest filters does anything appear at all, and then it appears strongly. That disappearance is a fingerprint. It means the light from this object has been stretched by the expansion of space until every trace of its blue has been dragged out past the reach of those filters. The stretching is enormous. The light arriving at Webb's mirror is roughly 15 times longer in wavelength than the light that left the source. Almost nothing else in the observable universe does that. Run the arithmetic backward, and the smudge turns out to be a galaxy that was already shining when the universe was about 290 million years old. The universe is now about 13.8 billion years old. So this thing existed when the cosmos had lived through roughly 2% of its life so far. If you compressed all of cosmic history into a single year, the light we are looking at left in the first week of January. That alone would be remarkable. Distance records are collected and broken. What made astronomers stop and reread the data was not the distance, it was the size. The galaxy measures more than 1,600 light-years across. That is a real, resolved extent, not a point of light, and across that entire span, it is pouring out the radiation of young, hot, massive stars, so many of them that the total starlight adds up to a few 100 million times the mass of our Sun locked into stars already made. At 290 million years old, the universe had barely finished being dark. Hydrogen had barely finished cooling. The theories that had guided galaxy formation for 30 years said the first structures should be small, dim, ragged things, still gathering themselves, still small enough to be swallowed by anything larger. Instead, there is a lit object 1,600 light-years wide, blazing. Stefano Carniani of the Scuola Normale Superiore in Pisa, one of the astronomers who confirmed it, and Kevin Hainline of the Steward Observatory in Arizona, who worked alongside him, both described what they were seeing as a surprise. The word that circulated afterward, in press coverage and in hallways, was harsher than that. To understand why a faint red dot unsettled people who study the universe for a living, you have to first understand the machine that saw it. the James Webb Space Telescope left Earth on Christmas morning, the 25th of December, 2021, on an Ariane 5 rocket from the launch complex at Kourou in French Guiana. It had been under construction, in one form or another, for close to 30 years. It cost roughly $10 billion. It was named after James Webb, the man who ran NASA through most of the 1960s. The telescope that lifted off that morning was folded up like origami because it could not possibly fit inside a rocket at its true size. The heart of it is a mirror 6.5 meters wide. That is wider than most rooms in most houses. It is not a single piece of glass. It is 18 hexagonal segments, each one about 1 1/3 meters across, fitted together into a shallow honeycomb. Each segment is made of beryllium, a light and unusually stiff metal that barely changes shape when it gets cold. Each is coated with a skin of gold about 1,000 atoms thick. All the gold on the entire mirror, added together, weighs about as much as a golf ball. Gold is there because it reflects infrared light better than silver or aluminum do. Infrared is the point. Infrared is the whole design. Light from the earliest galaxies arrives stretched into the infrared, and infrared is heat. A warm telescope glows in exactly the wavelengths it is trying to observe, the way a hot stove glows if you could see a little farther into the red. Webb cannot be warm. It has to be colder than nearly anything humans have ever flown. So underneath the mirror there is a sun shield, 5 separate layers of a plastic film called Captain, each layer coated with aluminum, each thinner than a human hair, unfurled to roughly the size of a tennis court. The layers do not touch. Heat leaks through the first layer, radiates sideways into the vacuum between the first and the second, and is mostly lost. Then the process repeats. By the 5th layer, almost nothing is left. The sun-facing side of that shield sits at about 85 degrees Celsius. The mirror side sits at roughly 40 degrees above absolute zero, which is about minus 233 Celsius. Between those two surfaces, separated by a few meters of aluminized plastic, there is a temperature difference of more than 300 degrees. For that arrangement to work, the Sun, the Earth, and the Moon all have to stay on the same side of the shield at all times. That means Webb could not orbit the Earth the way Hubble does, swinging in and out of daylight every 90 minutes. Instead, it flew out to a point about 1.5 million kilometers away, roughly 4 times farther than the Moon, called the second Lagrange point. There, the pull of the Earth and the pull of the Sun combine so that a spacecraft can keep pace with our planet as it circles. Webb does not sit exactly at that point. It traces a wide, slow loop around it, taking about 6 months to complete each circuit, firing its thrusters occasionally to stay in the loop. It carries no repairman's handholds. There was, at launch, a list of 344 single points of failure, places where one mechanism jamming would end the mission. 178 release devices had to fire in sequence. Over the 2 weeks after launch, the sun shield unfolded, the mirror wings swung into place, and every one of them worked. Then came the cooling, which took months, because a telescope that large sheds its warmth slowly. Only after all of that could the light be let in, and light, on its own, tells you very little. It has to be sorted. There are 4 instruments behind Webb's mirror, and each one takes the arriving light and asks it a different question. The first is NIRCam, the near-infrared camera, built under the direction of Marcia Ricci at the University of Arizona. It is the workhorse. It sees light from about 0.6 of a micron, at the very edge of what human eyes call red, out to about 5 microns, deep into the infrared. NIRCam does not simply take one picture. It takes pictures through a rack of filters, each filter passing only a narrow band of wavelengths. Compare the brightness across those filters, and you begin to learn the shape of an object's light, which is to say, its colour, in far finer detail than any eye could manage. NIRCam has a second job as well. It measures the shape of the mirror itself. During the months after launch, its images of a single star were used to nudge each of the 18 segments into alignment, actuator by actuator, until they behaved as one surface. The second instrument is NIRSpec, the near-infrared spectrograph, contributed by the European Space Agency and built largely by Airbus in Germany. A spectrograph spreads light out by wavelength, the way a prism spreads sunlight into a band of colour. That spread is where the real information lives, because atoms absorb and emit at exact wavelengths, and those wavelengths are a signature you can read. NIRSpec contains something that has no real precedent in space. It is called a microshutter array, a grid of roughly 250,000 tiny doors, each about the width of a strand of hair. Each door can be opened or closed on command by a magnet. That means astronomers can open a shutter over each galaxy they care about, close every shutter over empty sky, and take spectra of about 100 objects at once without their light bleeding together. The third instrument is MIRI, the mid-infrared instrument, built by a partnership between European institutions, NASA, and the Jet Propulsion Laboratory, with George Ricci and Gillian Wright leading the science teams. MIRI reaches from about 5 microns out to 28. To see light that long, its detectors have to be even colder than the rest of the observatory. A dedicated mechanical cryocooler pumps cold helium gas through it and holds it below 7 degrees above absolute zero. The fourth is NIRISS, the near-infrared imager and slitless spectrograph, contributed by the Canadian Space Agency under René Doyon at the Université de Montréal. It sits alongside the Fine Guidance Sensor, also Canadian, which locks onto guide stars and holds the entire telescope steady to a fraction of the width of a human hair seen from a kilometre away. Without that steadiness, long exposures would smear into nothing. Put together, the pattern of work goes like this. NIRCam finds candidates by their colours. NIRSpec is pointed at the most interesting of them and returns a spectrum which is proof. MIRI catches the light that has been stretched even further, the light that was visible when it left. NIRISS and the guidance sensor make the long stares possible. Every discovery in this story runs through that sequence. Find, confirm, extend. If you are enjoying this slow walk through what Webb has actually seen, subscribing helps the channel keep making these long, quiet nights of astronomy. The sequence produced its first public result on a summer evening in 2022, and the image that appeared surprised even the people who had spent their careers waiting for it. On the 11th of July, 2022 at the White House, a single image was shown before the rest were released the following day. It was a photograph of a cluster of galaxies called SMACS 0723 in the southern constellation Volans. The exposure had taken about 12.5 hours across several NIRCam filters. 12.5 hours is not, by the standards of this work, a long time. The Hubble Deep Field, taken in December of 1995 under the direction of Robert Williams, then the director of the Space Telescope Science Institute, consumed 10 straight days of observing on a piece of sky that many astronomers considered a waste of the telescope. Williams used his director's discretionary time to do it anyway. The image came back full of galaxies nobody had known were there. The Hubble Ultra Deep Field, taken in 2003 and 2004, went deeper still, gathering photons for the equivalent of 11 days. Webb reached comparable depth in half a day, and kept going. It helps to understand what a deep field actually is, physically. Light from a distant galaxy arrives at the mirror not as a continuous stream, but as a scattering of individual photons, one at a time, minutes or hours apart. A deep exposure is not a photograph in any everyday sense. It is a tally. The detector counts arrivals patiently, and at the end you have a map of how many photons fell in each pixel, over how many hours. The patch of sky in a deep field is tiny. The standard comparison, which happens to be accurate, is a grain of sand held at arm's length. Cover that much of the sky, stare through it long enough, and you find thousands of galaxies stacked behind one another at every distance. The SMACS image had another feature, and it was the reason that particular cluster was chosen. Around the crowded centre of the cluster, the background galaxies appeared bent, stretched into arcs, some smeared into long thin curves, some duplicated, the same galaxy appearing twice or 3 times in different places. The cluster's mass was warping the space around it and acting as a lens. That was a preview of a technique the deepest work would depend on. But the ordinary unlensed part of that image mattered more. Across it were small red objects, dozens of them, that had no counterpart in any of Hubble's images of the same region. They were not there because Hubble could not see them. Hubble's most sensitive infrared camera runs out of sensitivity somewhere around 1 7/10 microns. Beyond that, its detectors simply stop. Objects whose light has been stretched past 1 7/10 microns had been invisible to human beings entirely until Webb switched on. Not faint, not hard, invisible. Within days of the first data release, papers began appearing on the preprint servers claiming galaxies at distances nobody had expected to reach for years. Some of those claims held up, several did not. The whole field was moving faster than its own quality control, and the arguments that followed would take 2 years to settle. All of it depended on one measurement, made in one way, on light that had been travelling for almost the entire history of the universe. That measurement is called redshift, and it is worth slowing down to understand exactly what it is and what it is not. Imagine a wave of light leaving a hot star inside a young galaxy. It is ultraviolet, short and tight, the kind of light that would burn your skin in seconds. It sets out across space, and space, in the meantime, is expanding. This is the piece that trips people, so it is worth saying carefully. The galaxies are not flying apart through space like fragments of a grenade. The space between them is growing. Every distance is stretching. A wave of light travelling through that space has its own crests and troughs, pulled apart along with everything else. The wave arrives longer than it left. Longer wavelength, for light, means redder. Ultraviolet becomes violet. Violet becomes green. Green becomes red. Red becomes infrared. If the stretch is severe enough, the light passes out of the visible range entirely and can only be caught by an instrument cooled to 40 degrees above absolute zero. Astronomers describe the stretch with a single number, written as the letter Z. The rule is simple. Take the number, add 1, and that gives you the factor by which the wavelength has grown. A galaxy at a redshift of 1 sends light that arrives twice as long as it left. A galaxy at a redshift of 9 sends light that arrives 10 times longer. JADES-GS-z 14-0 sits at a redshift of 14.32. Its light arrives at Webb's mirror a little more than 15 times longer than it began. Follow one particular wave to see what that means. Hydrogen, the most common substance in the universe by far, emits a bright ultraviolet line at 121.6 nanometers. That is deep ultraviolet, far shorter than anything an eye can register, the kind of a light stopped dead by ordinary window glass. Multiply it by 15.32 and it arrives at about 1.86 microns. 1.86 microns is past Hubble's cutoff. It is comfortably inside NIRCam's range. That single number is why the last 4 years of cosmology happened. There is a second meaning hidden in redshift, and it is the more powerful one, because the stretch is caused by the expansion of space, and because the expansion has been going on since the beginning. The size of the stretch tells you how much the universe has grown since that light departed. A redshift of 14.32 means the universe has grown by a factor of 15.32 in every direction since that light left the galaxy. Every distance was 15 times smaller. Every volume was more than 3,000 times smaller. The whole cosmos was denser, hotter, and crowded together. So redshift is not really a distance measurement. It is a measurement of scale, and through scale, a measurement of time. Notice also what redshift does not tell you. It says nothing about how bright the galaxy truly is, nothing about how much mass it contains, nothing about what is producing the light. Those quantities have to be reasoned out afterward, from the shape of the spectrum and from a great many assumptions. Much of the fear and confusion in this story comes from that gap between what the number measures and what people wanted it to mean. Before any of that reasoning can begin, though, you have to find the galaxy at all. and you cannot spread every faint smudge in a deep field into a spectrum because there are far too many, and each spectrum costs hours. You need a shortcut, a way of picking the ancient galaxies out of a crowded picture, using nothing but their colours. Between the galaxies of the early universe there was hydrogen, not much of it by the standards of anything on Earth, but it filled the space between everything, and in those first few 100 million years it was neutral, meaning each atom held its electron. Neutral hydrogen has a specific appetite. It absorbs ultraviolet light at wavelengths shorter than that same 121.6 nanometer line, and it absorbs it greedily. A photon of light shorter than that wavelength travelling out from a young galaxy runs into hydrogen atom after hydrogen atom and is very unlikely to survive the trip, so the light that reaches us from a galaxy in the early universe has a cliff in it. On the long wavelength side of that hydrogen line, light passes through. On the short wavelength side, it is eaten. The spectrum falls off a shelf. That cliff is called the Lyman break, after Theodore Lyman, the Harvard physicist who first measured this series of hydrogen lines in the early 1900s. Now put the cliff and the redshift together, and a technique appears. The break sits at a fixed wavelength when the light leaves. As the light stretches on its journey, the break stretches with it. A galaxy at a redshift of 7 has its break sitting near 1 micron. A galaxy at a redshift of 11 has its break near 1.5 microns. A galaxy at a redshift of 14 has it near 1.86. Photograph the same patch of sky through a series of filters, from blue through red. The galaxy will appear in the filters that sit above its break, and it will vanish in every filter below it. It drops out. And the filter where it drops out tells you, approximately, how far the light has been stretched. Chuck Steidl, then at the Massachusetts Institute of Technology, and later at Caltech, worked this out in practice in the early 1990s, using it to find galaxies at a redshift of about 3. He called them Lyman break galaxies. The method was simple, cheap, and it worked, and it has been used ever since. What changed with Webb is only the wavelength at which the dropout happens, and the depth to which you can chase it. This gives you what astronomers call a photometric redshift. It is a distance estimated purely from colours. It is fast. You can compute it for every object in a deep field at once, and produce a list of hundreds of candidates in an afternoon. It is also, in a specific and dangerous way, a guess. The problem is that a Lyman break is not the only thing that can make a galaxy bright in the red filters and invisible in the blue ones. Dust does it too. Dust absorbs blue light and lets red light through, which is why sunsets are red. A galaxy stuffed with dust sitting at a modest distance can wear a disguise that from a distance looks exactly like a cliff. Old stars can do something similar. A galaxy full of aging red stars has a subtler break in its spectrum, caused by absorption in the atmospheres of those stars, and at the right redshift that break lands in the same filter where a young distant galaxy's break would land. 2 very different objects, the same colours. In the first years after Webb turned on, that ambiguity produced a public embarrassment that everybody in the field now remembers. In the summer of 2022, weeks after the first data arrived, a team led by Callum Donnan at the University of Edinburgh reported an object in the Sears survey field with a photometric redshift of about 16.4. If that number was right, the galaxy existed when the universe was around 250 million years old. It was fainter than expected, but plainly there, and it was called Sears, 93,316. Several independent groups reanalyzed the same images and found the same answer. The candidate appeared in press coverage worldwide. Astronomers began referring to it, half joking, as the galaxy that would break cosmology. Careful people said, in every interview, that this was a photometric estimate, and that only a spectrum could settle it. The following year, a team led by Pablo Arrabal-Haro at the National Optical Infrared Astronomy Research Laboratory pointed near-spec at it and took the spectrum. The galaxy sits at a redshift of 4.91, not 16, under 5. It is a dusty, vigorously star-forming galaxy, seen when the universe was already well over 1 billion years old, and its colours had been counterfeited by a combination of dust reddening and unusually strong emission lines from hot gas. Those emission lines landed inside particular NIRCam filters and boosted their brightness, which shifted the fitted shape of the spectrum, which shifted the fitted break, which shifted the answer by more than 11 in redshift. There was a further complication. In those first months, the calibration of NIRCam itself was still settling. Astronomers had ground-based estimates of how many electrons each detector produced per photon, but the real values only became known after the telescope was in space and had observed calibration stars. The early 0 points were off by amounts that were small in absolute terms and enormous in their consequences for the fitted colours of the faintest objects. Papers written in August of 2022 used numbers that were revised by October. The field learned 2 lessons, and both of them shape everything that follows. The first is that a photometric redshift is a hypothesis. It is a good hypothesis, correct most of the time, and it becomes wrong in exactly the cases that are most exciting, because the most extreme candidates are the ones most likely to be an ordinary object caught in an unlucky disguise. The second lesson is about how confirmation actually feels. When NIRSpec takes a spectrum of a genuinely distant galaxy, the result is not a subtle statistical preference. It is a sharp edge at a specific wavelength, and often next to it, a set of narrow emission lines from oxygen, from carbon, from helium, sitting at exactly the wavelengths those atoms produce, all shifted by the same factor. Several independent lines agreeing on one number. That kind of evidence does not evaporate on reanalysis, so the survey teams changed how they worked. NIRCam finds the candidates are ranked. NIRSpec spends its expensive hours on the best of them. Nothing is claimed as a record until the lines are there. Every galaxy discussed for the rest of this script has been through that process, which raises a plainer question about what the confirmed number actually buys you, because a redshift is a stretch factor, and a stretch factor is not yet an age. Turning a redshift into a time requires knowing how the universe expanded over its history, which requires knowing what the universe is made of. The standard description is called Lambda cold dark matter. It is a model with a small number of ingredients. Ordinary matter, the atoms in stars and planets and people, makes up about 5% of the total. Cold dark matter, some substance that has mass and gravity but does not interact with light, makes up about 27%. The remaining 68% is called dark energy, written as the Greek letter lambda, and it behaves as a property of space itself that pushes the expansion faster. Feed those proportions into Einstein's equations for a uniform expanding universe, and you get a curve. The curve tells you the size of the universe at every moment in its past. That curve is not guesswork. It is fitted to a great deal of data. The cosmic microwave background, mapped in exquisite detail by the Planck satellite between 2009 and 2013, constrains it tightly. So does the clustering of millions of galaxies in surveys like the Sloan Digital Sky Survey. So do the brightnesses of exploding white dwarf stars used as distance markers, which is how the acceleration was discovered in 1998. Run the curve backward from today, and it says the universe began 13.8 billion years ago. The Planck value is 13.80, give or take about 20 million years. Now take a redshift of 14.32. The curve says the universe was that size when it was about 290 million years old. Take a redshift of 11, and you get about 400 million years. Take a redshift of 6 when ionization was ending, and you get about 930 million years. Notice how compressed the early numbers are. The whole span from redshift 20 down to redshift 10, an enormous change in the state of the cosmos, covers less than 300 million years. The universe changed faster at the beginning than it has ever changed since. There is one genuine unresolved crack in this arithmetic. The present expansion rate, the Hubble constant, comes out around 67 kilometers per second per megaparsec when it is inferred from the microwave background, and around 73 when it is measured directly from nearby exploding stars by teams like the one Adam Rees leads at Johns Hopkins. Those two answers do not overlap within their stated errors. Nobody knows why. It is called the Hubble tension, and if it is eventually resolved by changing the physics of the early universe, some of the ages quoted here would shift by tens of millions of years. They would not shift by hundreds of millions. The early galaxies would still be early. There is one more consequence of the curve worth naming. Because space kept expanding while the light travelled, the galaxy that emitted that light is now much farther away than the distance the light covered. JADES-GS-z 14-0 is now roughly 33.5 billion light-years from Earth, even though its light has only been travelling for 13.5 billion years. It is also receding faster than light, and that breaks no rules, because nothing is moving through space at that speed. Space is simply growing everywhere at once, which leaves a stranger question. What was there in all the compressed and rapidly changing early time before any galaxy existed to send light at all? For the first few 100,000 years the universe was opaque. It was hot, and everything in it was ionized, meaning the electrons were not attached to nuclei but flying free. Free electrons scatter photons. A photon of light in that environment could travel only a short distance before being deflected, then deflected again and again. Light could not go anywhere. The universe glowed like the inside of a furnace, uniformly in every direction. Then it cooled. At an age of about 380,000 years, the temperature dropped to roughly 3,000 degrees, cool enough that protons could capture electrons and hold on to them. The free electrons vanished into atoms. Hydrogen became neutral, and in a span of a few thousand years the fog cleared. The light that had been bouncing endlessly was suddenly free to travel, and it has been travelling ever since. It fills the universe. It arrives at Earth from every direction at once, stretched by expansion from that furnace glow into microwaves, cooled from 3,000 degrees down to 2.725 degrees above absolute zero. Arno Penzias and Robert Wilson found it by accident in 1965 at Bell Labs in New Jersey, while trying to eliminate a persistent hiss from a horn antenna. They cleaned out pigeon droppings before they concluded the hiss was cosmological. It is the oldest light there is. And then, having released that light, the universe went dark. Consider the situation. Neutral hydrogen everywhere, thinly spread. No stars, because no stars had formed. No galaxies, no quasars, nothing hot, nothing burning, nothing radiating. The residual glow of the microwave background, red-shifting steadily out of the visible into the infrared and then away. Temperature falling, density falling. Astronomers call this the Dark Ages, and the name is literal rather than poetic. If you had been standing there, wherever there means, you would have seen nothing at all. Not blackness with distant lights. Blackness. The Dark Ages lasted somewhere between 100 and 200 million years, and possibly a little more. During that entire stretch, the only thing happening was gravity, working slowly and invisibly. Here is what gravity was doing. The early universe was not perfectly smooth. It had faint ripples in its density, 1 part in 100,000, imprinted before the microwave background was released and visible today as the slightly warmer and cooler patches in that background. Dark matter, which feels gravity and nothing else, began falling into the slightly denser patches. Those patches grew denser. They pulled in more. Over 100 million years, ripples became lumps and lumps became halos, invisible knots of dark matter with hydrogen gas pooling in their centres. The gas fell inward. It heated as it fell. It needed a way to shed that heat in order to collapse further, and hydrogen molecules, forming rarely in that cold gas, provided a slow and inefficient cooling channel. Somewhere inside one of those halos, the gas got dense enough and cold enough, and the first star ignited. Nobody has ever seen one. The first stars have a name, Population 3, which comes from a numbering scheme running backward. The stars around us today are population 1, rich in the elements that previous generations of stars made. The older, poorer stars in the halo of our galaxy are population 2. The stars that formed before any elements existed at all would be population 3. Their defining feature is what they lacked. The universe emerging from the Big Bang contained hydrogen, helium, and a trace of lithium. Nothing else. No carbon, no oxygen, no nitrogen, no iron. Astronomers call every element heavier than helium a metal, which annoys chemists, and by that definition the first stars had no metals whatsoever. That absence changes everything about how they formed. Metals are what allow a gas cloud to cool efficiently. Carbon and oxygen radiate away heat at low temperatures, letting a collapsing clump keep shrinking. Without them, a cloud of pure hydrogen and helium can only cool through those inefficient hydrogen molecules, and it stays warm. Warm gas resists collapse. It has to gather far more mass before gravity wins. The simulations, run by groups including Volker Brom at the University of Texas and Naoki Yoshida in Tokyo, suggest the result was stars of tens to hundreds of times the mass of the Sun. Enormous, blue-white, ferociously hot, radiating in the ultraviolet. Their lifetimes would have been short, measured in a few million years, because a star that massive burns through its fuel at a suicidal rate. Their deaths were unusual. A star between roughly 140 and 260 solar masses does not collapse into a black hole at the end. Its core becomes hot enough that photons spontaneously convert into pairs of electrons and their antimatter counterparts. That conversion removes pressure, the core contracts, and the star detonates completely. It leaves nothing behind. The whole thing is dispersed into space as elements. Astronomers call it a pair instability supernova. Those first deaths seeded the universe with the first oxygen and the first carbon. Every subsequent generation of stars formed from gas contaminated by them. The trouble is that nobody has confirmed a single population 3 star anywhere, ever. There have been candidates. In 2024, a team including Roberto Maiolino at Cambridge reported a clump of helium gas near the galaxy GN-z11 with no detectable heavy elements, which might be a pocket of pristine gas hosting such stars. In 2025, a heavily lensed object called ELAP-1-b was put forward as a candidate cluster. The evidence in each case is suggestive and contested. This matters for the story ahead, because everything the first stars did afterward depends on what they were. Their mass sets how much ultraviolet light they poured out. Their death set how quickly the universe was enriched with metals. Their remnants may be the seeds from which supermassive black holes grew, and their ultraviolet light did something to the universe as a whole, something that took hundreds of millions of years and left a signature we can still read in the spectra of distant quasars. It undid the neutrality of the hydrogen. It boiled the fog away. Ultraviolet light with enough energy can knock the electron off a hydrogen atom. The atom becomes a bare proton, and the electron goes free. Do that everywhere, to nearly all the hydrogen in the universe, and you have reionized it. That is the name for the process, and it is the last great transformation the cosmos has undergone. It did not happen all at once. It began as bubbles. Around each early source of ultraviolet light, whether a cluster of hot young stars or a growing black hole, the surrounding hydrogen was stripped bare out to some radius. Inside the bubble, light travelled freely. Outside it, the neutral hydrogen still absorbed. As more sources lit up, the bubbles grew and began to touch, then merge, until at last the ionized regions connected across the entire universe, and the neutral patches were the isolated ones. The whole process seems to have run from perhaps 200 million years to about 1 billion years after the beginning, ending somewhere near a redshift of 6. We know when it ended because of a signature in quasar spectra. A quasar is a supermassive black hole feeding voraciously and shining brighter than its entire host galaxy. Look at a distant one, and its light has passed through everything between it and us. If the intervening hydrogen was neutral, the light shortward of the Lyman break gets absorbed away entirely, leaving a black stretch in the spectrum. James Gunn and Bruce Peterson predicted this in 1965. For decades, no quasar showed it. Then in 2001, Robert Becker, Xiaohui Fan, and their colleagues, working with the Sloan Digital Sky Survey, found quasars beyond a redshift of 6, whose spectra went dark exactly where predicted. The last of the neutral hydrogen was there, and they had found the edge of it. The harder question is what supplied the ultraviolet light. Quasars are powerful, but there do not seem to be nearly enough of them at that epoch to do the job. The favoured answer for 20 years has been faint galaxies, enormous numbers of them, each one modest but collectively adequate, provided that a decent fraction of their ultraviolet photons escape rather than being reabsorbed inside the galaxy itself. That escape fraction is the sticking point. It cannot be measured directly at high redshift, because the escaping photons are precisely the ones the intervening hydrogen destroys. It has to be inferred from lower redshift analogues and from indirect indicators. Webb has pushed on this. Deep observations behind lensing clusters, led by teams including Hakima Tech at the Institut d'Astrophysique de Paris, have found the faint galaxy population to be more numerous and more efficient than the earlier estimates allowed, enough to finish the job. Other work has argued that a population of small, obscured black holes contributed meaningfully. The accounting is not closed. What Webb has settled is that the sources were already in place remarkably early. The galaxies were there. They were bright. They were producing ionizing radiation while the universe was still a toddler. Seeing them at all, though, has often required help. The faintest of these objects lie beyond the reach even of a 6.5 metre mirror, and astronomers have learned to borrow a lens that no one built. In 1936, Albert Einstein published a short paper in the journal Science, at the urging of a Czech engineer named Rudy Mandl, showing that a massive object would bend light passing near it and could focus that light like a lens. Einstein added with some resignation that there was no great chance of observing the phenomenon. He was thinking of individual stars. He had not considered clusters of galaxies, which is what Fritz Zwicky pointed out 2 years later. A galaxy cluster is the largest gravitationally bound structure in the universe, containing hundreds or thousands of galaxies, an ocean of hot gas, and a vastly larger quantity of dark matter. Its total mass warps the space around it. Light from anything directly behind it takes a curved path on its way to us and arrives magnified, distorted, and sometimes multiplied into several images of the same object. Point Webb at a cluster, and you're pointing it through a telescope that nature built and left running. The gains are extraordinary. A well-placed background galaxy can be magnified by a factor of 10 or 50, or in rare geometric alignments by thousands. Objects that would be undetectable in an ordinary field become measurable. Abell 2744 in the constellation Sculptor is the most studied of these lenses. It is a wreck of at least 4 galaxy clusters colliding, which earned it the name Pandora's Cluster. The Hubble Frontier Fields program spent hundreds of orbits on it, and 5 other clusters between 2013 and 2017 precisely to exploit the magnification. The most extreme case yet found sits behind a cluster called WHL 0137-08. In 2022, a team led by Brian Welch, then at Johns Hopkins, reported that a single star, magnified by a factor of several thousand by a fold in the lens, was individually visible at a redshift of about 6.2. They named it Earendel, from an Old English word for morning star. It is the most distant individual star ever seen. Webb has since observed it and found it to be hot, massive, and probably not alone. Lensing has produced other strange objects. The Cosmic Gems arc, reported by Angela Adamo at Stockholm University in 2024, shows a galaxy at a redshift of 10.2 stretched into a long ribbon, inside which sit 5 compact star clusters, each one dense enough to be a globular cluster in the act of forming. The Firefly Sparkle, described by Lamia Mola at Wellesley College the same year, is a galaxy at a redshift of 8.3 resolved into 10 separate clumps of star formation, weighing about as much as our own galaxy did at that age. There is a cost. Every lensed measurement depends on a model of the cluster's mass distribution, and different modelling teams produce different magnifications for the same object, sometimes differing by a factor of 2. A galaxy's inferred brightness inherits that uncertainty directly, which is why the objects that unsettled the field most were not the lensed ones. They were bright enough to be found in blank sky, with no lens at all, and the first of them had been sitting in Hubble's images for years. In 2016, Pascal Oesch, then at Yale and now at the University of Geneva, published a measurement that most of his colleagues considered improbable. Using Hubble's Wide-Field Camera 3 in a mode called GRISM spectroscopy, which spreads light into a low-resolution spectrum across the detector, Oesch and his collaborators found a break in the light of an object in the Goods North Field in Ursa Major. The break implied a redshift of 11.1. That was a full unit beyond anything previously confirmed, and it was right at the edge of what Hubble could physically do. The object was called JWST. Its inferred brightness was awkward. It appeared to be about 20 times more luminous than the typical galaxy at its epoch, and there was no obvious reason for such a thing to exist 400 million years after the beginning. Several astronomers suggested the break was a mirage, an ordinary dusty galaxy at a redshift of 2 or 3 whose colours happened to line up. The measurement rested on a single feature, at low resolution, at the limit of the instrument. For 6 years the question stayed open. In 2022, within months of Webb becoming operational, NearSpec was pointed at JWST, and the spectrum came back covered in emission lines: carbon, neon, oxygen, nitrogen. Each line at exactly the wavelength that atom produces, each stretched by the same factor. The redshift is 10.6, slightly lower than Hubble's estimate and completely real. The universe was about 430 million years old. Then the spectrum kept giving. The nitrogen lines were far stronger than expected relative to the oxygen lines, indicating a chemical composition unlike almost any galaxy known, and resembling in that one respect the oldest globular clusters in our own galaxy. Something had enriched this gas with nitrogen very rapidly. The gas density in the central region came out extraordinarily high, hundreds of times denser than the star-forming clouds of the Milky Way. The galaxy itself is small. Its stellar body spans a few hundred light-years, which would fit comfortably inside the space between the Sun and the nearest few hundred stars. And in 2024, a team led by Roberto Maiolino at Cambridge found something in the centre of it, a set of broad emission lines, meaning gas moving at thousands of kilometres per second, which is the signature of material whipping around a black hole. From the width of those lines and the brightness of the source, they derived a mass of roughly 1.5 to 2 million times the Sun. A black hole the mass of 1.5 million suns, 430 million years after the universe began, sitting inside a galaxy only a few hundred light-years wide. Nobody had a comfortable explanation for that, and JWST was, at the time, considered the safe and well-understood case. The objects Webb was about to find in its own surveys were harder. The first of them was found by accident, in the ordinary process of sifting a survey, and it acquired a name that has nothing to do with catalogues. The survey is called CEERS, the Cosmic Evolution Early Release Science Survey, led by Stephen Finkelstein at the University of Texas at Austin. It targeted a strip of sky in Ursa Major called the Extended Groth Strip, which Hubble had already imaged deeply. CEERS was designed to be fast, public, and useful, with the data released to everyone immediately, so the community could learn how to work with a new telescope. In June of 2022, Finkelstein was going through the first NIRCam images and found an object that had dropped out of the shorter filters. Its colours implied a redshift somewhere near 14. He noticed the date. It was his daughter Maisie's birthday. Maisie's galaxy entered the literature under that name. The initial photometric estimate proved too high, as photometric estimates of extreme objects tend to be. When NIRSPEC observed it, in work published in 2023 by the team led by Pablo Arrabal-Haro, the spectrum returned a redshift of 11.44. The universe was about 390 million years old. That is lower than 14. It is also, in every way that matters, still a stunning result. The galaxy was confirmed, its lines were clean, and it exists at a time when the models had expected almost nothing to be visible at that brightness. The broader Sears analysis was where the discomfort began. Finkelstein's group counted the bright galaxies they were finding in the redshift range between 9 and 16, and compared that count against what the standard models predicted. There were too many, not slightly too many. At the bright end, the models undercounted by a factor of 10 or more. The models in question were not casual sketches. They combined cold dark matter simulations, which are trusted, with recipes for how efficiently gas turns into stars inside a dark matter halo, recipes calibrated against every galaxy survey of the previous 20 years. Those recipes said that at early times a halo of a given mass should convert only a small percentage of its gas into stars, because supernovae from the first stars blow the remaining gas out and shut the process down. Take that constraint seriously, and there is a ceiling on how bright a galaxy can be at a given age. Sears found galaxies above the ceiling. Finkelstein was careful in how he framed it, and consistently said that the models were the likeliest thing to be wrong, not cosmology itself. Other groups reporting similar excesses were less careful, and the phrase that reached the public was that the Big Bang theory was in trouble. It was not in trouble. The measurements were about galaxies, and the models being strained were models of star formation which sit several layers above the cosmological framework and were always known to be the shaky part. But something had to change, and while the arguments over Sears ran, a much deeper survey was quietly gathering the data that would push the boundary further than anyone had planned. JADES stands for the JWST Advanced Deep Extragalactic Survey. It is a joint program of the NIRCam and NIRSPEC instrument teams, which meant it was built by the people who had spent decades constructing the hardware and who had been guaranteed observing time in exchange. Daniel Eisenstein at the Center for Astrophysics in Cambridge, Massachusetts, and Marcia Ricci, the same astronomer who led NIRCam, co-directed it. Brant Robertson at the University of California, Santa Cruz, led much of the analysis of the earliest galaxies. Roughly 800 hours of observing time were committed, spread over the two goods fields, north and south. The design philosophy was patience. Rather than chasing headlines with shallow, wide imaging, JADES went deep on small areas and paired every deep image with spectroscopy. The imaging was taken through 9 or more NIRCam filters, so that the shape of each galaxy's light could be traced finely enough to catch a break in the right place. Then the microshutter array was opened over hundreds of targets at once, and NIRSPEC stared for tens of hours. The first major result appeared in 2023. Emma Curtis Lake at the University of Hertfordshire and her colleagues published spectroscopic confirmations of 4 galaxies beyond a redshift of 10. Their redshifts were 10.38, 11.58, 12.63, and 13.20. The last of those, called JADES-GS-z 13-0, held the distance record for a year. Its light left when the universe was about 320 million years old. What struck the team about all 4 was their size. They were tiny. Their light was concentrated into regions a few hundred light-years across, which is smaller than many star-forming complexes inside the Milky Way today. They were compact, ultraviolet bright, and they showed almost no dust. That combination made sense. A small galaxy, a burst of new stars, clean gas, no time yet for dust to accumulate. The models could accommodate objects like that with some stretching. Then JADES went deeper still. Within the good south field, the team defined a smaller region called the JADES Origins Field and poured observing time into it, building up an image with an exposure equivalent to more than 300 hours of staring. It is the deepest infrared image of the sky that exists. In that image, in October of 2023, NIRCam recorded a source that had dropped out of every filter below about 2 microns. its photometric redshift fitted at around 14.4. It was bright, brighter than anything the survey had confirmed, and unlike the earlier record holders, it was not a point of light. It had visible extent. The team looked at the number, looked at the brightness, and understood that if it was real, they were going to have to explain it. They scheduled NER spec. In January of 2024, the microshutter opened over that source and stayed open for close to 10 hours. 10 hours of collecting individual photons from an object whose light had been travelling for 13.5 billion years. Over that stretch, Webb's guidance sensor held the telescope steady, the cryocooler hummed, and the counts accumulated one at a time. When the spectrum was extracted, it showed a clean, sharp break. Below 1.8 microns, nothing. Above it, a continuum of light that ran smoothly out toward the red. The break sat exactly where hydrogen absorption would put it, for a galaxy at a redshift of 14.32. The uncertainty on that number is about plus 0.08 and minus 0.20. It is not a guess, it is a measurement. The universe was 290 million years old. The result was announced at the end of May 2024 in a paper led by Stefano Carniani in Pisa, with Kevin Hainline of the University of Arizona as a co-lead on the companion analysis. The object, JADES-GS-z 14-0, immediately became the most distant galaxy ever confirmed, beating the previous record by more than 1 full unit in redshift. 2 further pieces of evidence arrived to nail it down. Jake Helton, also at Steward Observatory in Arizona, checked whether MIRI had captured the source. MIRI sees light between 5 and 28 microns. At this galaxy's redshift, that range corresponds to light that was ordinary visible light when it left. Helton found the galaxy in the MIRI data at 7.7 microns, and it was brighter there than a smooth continuum would predict. That excess is the fingerprint of strong emission lines from hydrogen and oxygen, boosting the brightness inside that filter's band. Then, ALMA, the array of radio dishes on the Chasnanto Plateau in Chile, was pointed at it. ALMA detected a specific emission line from doubly ionized oxygen at a rest wavelength of 88 microns, arriving stretched into the millimeter range. 2 teams, one led by Sander Skaus in Leiden and one by Stefano Carniani, published the detection in 2025. It gives an independent spectroscopic redshift of 14.18, 3 instruments on 2 continents and 1 spacecraft, 3 different physical processes, 1 answer. Now consider what the brightness implies. To shine that intensely at that distance, the galaxy must be pouring out ultraviolet light at a rate that requires several 100 million solar masses of stars, most of them young. It is forming new stars at something like 20 times the rate the entire Milky Way manages today, inside a volume smaller than one of our spiral arms. Carniani, describing it afterwards, said the surprise was not that a galaxy existed at that age. Everyone expected galaxies. The surprise was that this one was so bright, so large, and so evidently made of stars. That last word, stars, is doing enormous work in the sentence, proving it required one more measurement, and it came not from the spectrum but from the shape of the light on the detector. There is a rule about telescopes that no engineering can escape. Light passing through an aperture of a given size can never be focused to a point sharper than a certain angular width, set by the wavelength of the light and the diameter of the mirror. For Webb, at 2 microns, that limit is around 6/100ths of an arcsecond. An arcsecond is 1/3600th of a degree. Hold a coin at a distance of 4 kilometers, and it subtends about that angle. Anything smaller than the limit appears as a fuzzy disk of exactly the same shape, no matter what it truly is. A star, a point-like black hole, a compact knot of anything, all produce the same identical pattern. Anything larger than the limit does not. It looks broader than the pattern. JADES-GS-z 14-0 looks broader. When the NIRCam images are compared against the instrument's known response to a point source, this galaxy is measurably extended. Fitting a light profile gives a half-light radius of about 260 parsecs, which converts to roughly 850 light-years. The full extent of the visible light, the thing the discovery papers quoted, is more than 1,600 light-years across. Sit with that measurement for a moment, because it is the hinge of this entire story. 13.5 billion light-years away, in a universe 15 times smaller than the present one, Webb resolved a structure. Not detected, resolved. It measured a shape. The distance from our Sun to the Orion Nebula is about 1,300 light-years. The galaxy is wider than that. The nearest globular cluster, Messier 4, has a diameter of about 70 light-years. This object is more than 20 times wider. It is small compared with the Milky Way, which spans 100,000 light-years or more. But it is a real, extended, structured thing, not a single burst of light from one place. Now here is the consequence, and it is the reason the size measurement was reported in the very first sentences of the announcement. A supermassive black hole feeding at maximum rate can produce the light of an entire galaxy. If the brightness of this object came from an accreting black hole, the explanation for its luminosity would be easy, and no theory of star formation would be threatened at all. Black holes are compact. The region producing that light would be smaller than a light-year across, and Webb would see a point source. Webb sees 850 light-years of half-light radius. The light is spread across a region far too large for any black hole to illuminate. It is coming from stars, distributed across the body of a galaxy. The spectrum agrees, showing narrow emission lines rather than the broad ones that fast-moving gas near a black hole produces. So the brightness has to be paid for in stars. Hundreds of millions of solar masses of them, assembled and ignited inside a universe not yet 300 million years old, in a galaxy that had to first gather its gas, cool it, collapse it, and form generation upon generation of stars fast enough to have already produced the oxygen that Alma can see. The models had a ceiling, and this object sits above it, with its shape measured and its distance confirmed 3 separate ways. It also, within a year, lost its record. On the 16th of May 2025, a NIRCam image came down from a survey with an unusually honest name. It is called Mirage or Miracle. Rohan Naidu, an astronomer at the Massachusetts Institute of Technology, led it, and the name was chosen because the field had already been burned once. Every candidate at these redshifts is either a genuine object from the first 300 million years, which would be a miracle of early growth, or an ordinary galaxy wearing a disguise, which would be a mirage. The survey was designed to separate the two by taking spectra of everything, immediately, without waiting. The target field was the Cosmos Legacy Field, a large patch of sky in the constellation Sextans that has been surveyed by nearly every major telescope. It covers about 2 square degrees, roughly 10 times the area the full moon covers on the sky, which makes it wide rather than deep. Wide surveys find rare bright things. Deep surveys find common faint things. In that image there was a source that vanished below 1.8 microns and appeared above it, exactly the signature the whole enterprise depends on. Its name is MOMS 14. NearSpec confirmed it at a redshift of 14.44, and the confirmation did not rest on the Lyman break alone. The spectrum carries emission lines from carbon, nitrogen, helium, and oxygen in several ionization states, all stretched by the same factor of 15.44. The peer-reviewed paper appeared in the Open Journal of Astrophysics in January of 2026, under a title that borrowed the survey's language and called the galaxy a cosmic miracle. Its light left about 280 million years after the beginning. 98% of the history of the universe has happened since. So JADES-GS-z 14-0, which had held the record for a year, was displaced by roughly 10 million years of cosmic time. That is a small change in absolute terms, and it is not the interesting part. The interesting part is that MOMS 14 is not built like its predecessor. It is compact. fitting its light gives an effective radius of about 240 light-years, with an uncertainty of a few dozen. The earlier record holder spread its starlight across more than 1,600 light-years. This one packs a comparable outpouring of ultraviolet light into a region several times smaller in radius, which means many times smaller in volume, and it is luminous, extraordinarily so, bright enough that finding it in a 2-square-degree field, rather than in one of the deep pencil beam surveys, tells you something on its own. Objects this bright at this redshift were supposed to be so rare that a survey of this size should have found none. 2 galaxies, 10 million years apart at the outer edge of what any instrument has ever seen. One diffuse and extended, one tight and blazing, both far brighter than the models permitted, and neither showing the broad emission lines that would let an accreting black hole take the blame. There is a third object worth naming, JADES-GS-z 14-1, confirmed at a redshift of about 13.9, sitting in the same deep image as its more famous neighbour. 2 galaxies at redshift 14 in one small field. The deep image was not supposed to contain even one. Naidu, asked what he made of it, said the early universe Webb is showing us does not look like what the models predicted, and that he found this both difficult and exciting. The records will move again. That is not the problem. The problem is that every time the boundary is pushed outward, something bright is already standing there, and the counting of bright things had gone wrong 2 years earlier in a paper that reached the front pages of newspapers under a phrase nobody involved had intended. In February of 2023, the journal Nature published a paper by Ivo Labbé, then at Swinburne University of Technology in Melbourne, with a long list of co-authors including Erica Nelson at the University of Colorado. The paper reported 6 red, compact objects found in the Sears imaging, with photometric redshifts between about 7 and 9. Their colours were unusual. They were faint in the blue filters and strikingly bright in the reddest ones, and when the shape of their light was fitted with standard models of stellar populations, the fits returned enormous masses. Several came out near 100 billion times the mass of the Sun in stars. That is the stellar mass of the Milky Way today, in galaxies seen when the universe was 500 million to 700 million years old. Nelson, quoted by the university's press office, said that if the masses were right, the objects should not exist, and used a phrase that ran around the world. She called them universe breakers. The claim was arresting because of a simple accounting argument. Ordinary matter makes up about 16% of all matter in the universe, the rest being dark. A dark matter halo assembling at high redshift can capture at most its share of ordinary matter. Even if every single atom that fell into the halo were converted into stars with perfect efficiency, wasting nothing, there is a hard ceiling on the stellar mass a halo of a given size can hold at a given cosmic time. Michael Boylan-Kolchin, at the University of Texas at Austin, worked through the arithmetic and published it the same year. The most extreme of the reported candidates sat close to that ceiling, or above it, depending on how the numbers were pushed. Not close to the ceiling on plausible star formation efficiency, close to the ceiling on the total supply of atoms. If that had held, the problem would not have been star formation. It would have been cosmology. It did not hold. The paper itself, read carefully, said as much. Labbé and his co-authors listed alternative explanations in the text, noted that the redshifts were photometric, and stated that spectroscopy was required. The press coverage removed the caveats. Spectroscopy arrived over the following 2 years, and it demolished the extreme interpretation in a way nobody had quite predicted. One of the 6 was observed with NR spec and found to sit at a redshift of 5.6, not 8, and it was not a galaxy full of ancient stars at all. Its spectrum showed broad emission lines from hydrogen, gas moving at thousands of kilometers per second, the signature of a black hole feeding at the center. The reddening that had been interpreted as a mountain of old stars was partly dust and partly light from an accreting black hole, and the mass in stars was a small fraction of what had been fitted. The others resolved similarly, lower redshifts than estimated in some cases, black holes contributing light in others, stellar masses revised downward by factors of 10 or more. Nothing broke. The universe was never in danger. What broke was a step in the reasoning, a step so routine that it is performed thousands of times a year without comment. Somebody had taken the brightness of an object and converted it into a mass. The conversion is where every assumption hides, and it deserves a careful look, because the same step underlies every number quoted so far. Suppose you are handed a photograph of a lit window at night and asked how many light bulbs are inside. You cannot see the bulbs. You can measure the total light and the colour of the light, and you know roughly how much light a bulb of each colour produces. Divide the total by the per bulb figure and you have an answer. But if the room contains one enormous floodlight rather than 40 small lamps, you will be badly wrong. If there is a curtain over the window absorbing half the light, you will be wrong again in the other direction. Measuring the stellar mass of a distant galaxy is that problem, with the curtain and the bulbs both unknown. The procedure has a name: spectral energy distribution fitting. You take the galaxy's brightness in every filter, which gives you the shape of its light across wavelength. Then you build model galaxies inside a computer, each one specified by a set of choices, and you ask which model produces a shape that matches. The choices are the problem. First, you must choose how many stars of each mass are born together, which is called the initial mass function. In the nearby universe, for every star born with the mass of the Sun, there are hundreds born smaller and a handful born larger. Massive stars are rare and enormously bright. A single star of 30 solar masses can outshine 100,000 stars like the Sun. So a galaxy's light is dominated by objects that contribute almost nothing to its mass, and the ratio between what you see and what is there depends entirely on this assumed distribution. Second, you must choose a star formation history. Did the galaxy build steadily, or in a single recent burst? A burst of new stars is blindingly bright and weighs very little. A steady old population is dim and heavy. The same brightness can correspond to masses differing by a factor of 30 depending on which history you assume. Third, dust. Dust absorbs blue light and re-emits it in the far infrared, outside Webb's reach. To account for the absorbed light, you assume a reddening law, a curve describing how much dust absorbs at each wavelength, calibrated on the Milky Way and on nearby starburst galaxies. There is no guarantee that the dust of a 300 million-year-old galaxy, made by supernovae of a kind that no longer occur, resembles ours. Fourth, gas. Hot ionized gas around young stars emits its own light in bright, narrow lines. In these early galaxies, those lines are so strong that they can contribute a substantial fraction of the light in a filter. Fit that as starlight, and you will invent stars that are not there. Fifth, and worst, outshining. Young stars are so much brighter than old ones that a small recent burst can hide an older population entirely underneath it. The old stars are present. They contribute mass. They contribute almost no light. You cannot measure what you cannot see. Publicly available codes exist to do the fitting. Prospector, Bagpipes, Beagle. They are good software, written by careful people, and they all report uncertainties. Those uncertainties are honest about the noise in the data. They are silent about whether the assumptions themselves are correct. Which brings us to the sentence that resolves most of this story, and it can be stated in 5 words. Brightness is not mass. An object can be extremely luminous and contain very little material, if the material it contains happens to be arranged in a way that produces light efficiently. This is not a technicality. It is the central correction, and once you hold it, most of the alarm drains out of the last 4 years. Consider what actually gets measured when Webb finds an early galaxy. NIRCam records how many photons arrive in each filter. NIRSpec records where the break falls and where the emission lines fall. Those measurements give you 2 things with real confidence: the redshift, which is to say, the epoch, and the ultraviolet luminosity, which is to say how much ultraviolet light the galaxy is producing right now. Ultraviolet luminosity has one dominant source: hot, massive, young stars. stars above roughly 10 times the mass of the Sun, burning at surface temperatures of tens of thousands of degrees, living for a few million years and then dying. Every one of those stars is a flare. Collectively, they set the ultraviolet brightness of a galaxy almost completely, and they contribute a few percent of its mass. So a galaxy's ultraviolet brightness is a measurement of its star formation rate over roughly the last 10 million years. It is a snapshot of an instant. It says nothing directly about the previous 280 million years. Now revisit what the surveys reported. Sears found more bright galaxies at redshift 10 than models predicted. JADES found a galaxy at redshift 14 with a large ultraviolet luminosity. MOMS 14 is enormously ultraviolet bright. Every one of those statements is about ultraviolet luminosity. Not one of them is directly about mass. The models being contradicted in turn predicted ultraviolet luminosity by taking a halo mass, multiplying by an assumed star formation efficiency to get a star formation rate and converting that rate into ultraviolet light. 3 steps. The first is well grounded in dark matter simulations. The second and third are calibrated on galaxies that existed billions of years later. If those early galaxies were forming stars in short, violent bursts rather than steadily, they would be brighter at any moment than a steady model predicts without being more massive. If they were making a larger share of massive stars than galaxies do today, they would be brighter per unit of mass. If they had not yet accumulated dust, more of their ultraviolet light would escape rather than being absorbed. Each of those possibilities produces exactly the observation, and none of them requires a single extra atom. The Universe Breaker episode was a case of the assumption failing catastrophically. The record-holding galaxies are a case of the assumption failing gently. In both instances, the fault sits in the machinery that turns light into stars, and that machinery was always the least certain part of the chain, which does not make the observations boring. Something is going on in those first 300 million years that does not happen later, and the 3 explanations just listed are not idle. Each one is a real physical proposal with simulations behind it, and one of them has begun to look more likely than the others. It starts with the recognition that early galaxies may not have been shining steadily at all. Imagine a galaxy that does not glow. Imagine that it flickers. Here is the physical picture. A small dark matter halo pulls in a reservoir of gas. The gas settles, cools, and collapses into stars. Within a few million years, the most massive of those stars reach the ends of their lives and explode. Supernovae inject energy into the surrounding gas, heating it and driving it outward. In a small halo, with weak gravity, that outflow can eject much of the remaining gas entirely. Star formation stops. The galaxy fades. Then, over tens of millions of years, gravity slowly pulls the ejected gas back in, along with fresh gas from the surrounding filaments. The reservoir refills. Another burst ignites. Galaxies at low mass do this. It has been seen in simulations for years, particularly in the FIRE project run by Philip Hopkins at Caltech, and collaborators including Claude-André Faucher-Giguère at Northwestern. Dwarf galaxies in the nearby universe show the fossil evidence of it in the ages of their stars. Now apply it at redshift 12, where every galaxy is low mass and the dynamical times are short. The whole population would be flickering, each galaxy spending some time bright and some time dim. A survey catches whichever galaxies happen to be bright when the shutter opens. This changes the counting in a way that is easy to underestimate. The number of dark matter halos falls very steeply with mass at these early epochs. There are vastly more small halos than large ones. If every halo's brightness fluctuates up and down, then the bright end of the observed population is filled not by the rare massive halos, but by the far more numerous small halos that happen to be caught mid-burst. Steep mass function plus scatter equals an excess at the bright end. The mathematics is the same as the reason that record-breaking performances in any large population come from lucky moments rather than from the top performers alone. Groups led by Charlotte Mason at the Cosmic Dawn Center in Copenhagen, by Jordan Marosha, and by others have shown that a scatter of roughly 1 magnitude in ultraviolet brightness, which is a factor of about 2.5, reproduces the observed excess without changing anything about cosmology. Avishai Deckel at the Hebrew University of Jerusalem proposed a sharper version. In the dense, gas-rich conditions of the early universe, he argued, gas clouds collapse and form stars faster than massive stars can live and explode. The feedback arrives too late to matter. Star formation runs unchecked until the gas is consumed, converting a large fraction of the reservoir into stars rather than the few percent that later galaxies manage. He called it a feedback-free starburst. If that is what happened, early galaxies were not merely flickering. They were, for brief intervals, converting gas into stars at efficiencies unmatched at any later time in the history of the universe. Both pictures predict something checkable. The bright early galaxies should be young, dominated by stars only a few million years old, with the emission lines of hot gas blazing across their spectra. That is what the spectra show. And both pictures leave a second question open. In a burst that violent, in gas with no metals and no dust, what kinds of stars actually form? The initial mass function is one of the quiet load-bearing walls of astrophysics. Edwin Salpeter, at Cornell, measured it first, in 1955. Counting stars in the solar neighbourhood, he found that the number formed at each mass follows a steep decline. For every star of 100 solar masses, there are millions of stars smaller than the Sun. That distribution has been remeasured many times, in the Milky Way's disk, in its halo, in nearby dwarf galaxies, in the Magellanic Clouds. It comes out roughly the same everywhere it can be checked, which is a strange and unexplained fact. Every star-forming region that has ever been examined closely, however, is contaminated by heavy elements from previous generations. Theory says the mass function should depend on the temperature of the gas from which stars condense. A collapsing clump fragments when its self-gravity overwhelms its internal pressure, and the mass at which that happens scales with temperature. Colder gas fragments into smaller pieces, warm gas fragments into larger ones. Metals let gas cool. Metals also make dust, and dust radiates heat away efficiently, and dust grains provide the surfaces on which hydrogen molecules form. Strip out the metals and the gas cannot get as cold. The fragments come out heavier. So the expectation, from theory alone, is that the first generations of stars were more massive on average than the stars around us. Not necessarily as extreme as pure population 3, which may have reached hundreds of solar masses, but shifted upward. Astronomers call such a distribution top-heavy. The consequences for what Webb sees are direct. A top-heavy population produces far more ultraviolet light per unit of stellar mass. The relationship is steeply nonlinear, because luminosity rises roughly as the third or fourth power of a star's mass. Shift the distribution modestly toward higher masses, and the ultraviolet output per solar mass of stars can rise by a factor of several. A galaxy could then be as bright as JADES-GS-z 14-0, while containing considerably less stellar mass than a standard fit would report. Dust matters in the same direction. In the local universe, roughly half of all the ultraviolet light produced by young stars is absorbed by dust before it escapes, and re-radiated in the far infrared. Astronomers correct for this routinely. But dust must be manufactured, in supernovae and in the winds of dying stars, and manufactured dust must have time to accumulate. A galaxy 290 million years old has had few generations of stars to make any. The spectra of the earliest confirmed galaxies show very blue ultraviolet slopes, consistent with little or no dust absorption. Some are among the bluest objects ever measured. Little dust means nearly all the ultraviolet escapes. The galaxy looks brighter to us not because it makes more light, but because it hides less of it. Combine the three effects. Bursty timing catches galaxies at their peak. Top-heavy stars produce more light per unit mass. Absent dust lets that light out. Multiply them together and the factor of 10 excess that alarmed everyone in 2022, becomes ordinary astrophysics operating under unfamiliar conditions, except that there is a fact in the data which none of that quite accounts for, and it concerns not the light but what the light passes through. The ALMA observation of JADES-GS-z's 14-0 detected oxygen, specifically a line emitted by oxygen atoms that have been stripped of 2 electrons at a rest wavelength of 88 microns. In that galaxy, 290 million years after the beginning, there is enough oxygen present and enough energy to ionize it that a radio array in the Atacama Desert can register the glow. Oxygen does not come from the Big Bang. Hydrogen and helium do, and a whisper of lithium. Everything else in the periodic table was assembled inside stars. Oxygen is built in the cores of massive stars during the phase in which they fuse helium and carbon, and it is released when those stars explode. To have oxygen in your interstellar gas, you must have formed massive stars, waited for them to live out their lives and had them die and disperse. A star of 20 solar masses lives roughly 10 million years. A star of 100 solar masses lives roughly 3 million. So the minimum time from a galaxy's first stars to its first oxygen is a few million years, plus however long the explosive debris takes to mix into the surrounding gas. That fits inside 290 million years easily. It is not the timing that surprised people, it is the amount. The team that analysed the ALMA detection, working alongside a second group led by Sander Scholes in Leiden, found the galaxy's oxygen abundance to be within a factor of a few of the sun's, and the 2 independent analyses disagreed about the exact figure, but agreed that it was far higher than the models of chemical enrichment had projected for that epoch. Stefano Carniani described the situation by comparing it to finding an adolescent where you expected an infant. Then look at what the other early galaxies contain. GN-z 11 at redshift 10.6 shows nitrogen lines so strong relative to its oxygen that its composition resembles almost nothing else known, except the peculiar chemistry recorded in the oldest globular clusters of the Milky Way. Something dumped a great deal of nitrogen into that gas very quickly. Candidate explanations include supermassive stars of thousands of solar masses, briefly alive, shedding processed material. MOMSI 14 at redshift 14.44 shows carbon, nitrogen, helium and oxygen. All 4, 280 million years in. The galaxy called GHZ2 at a redshift of about 12 shows a spectrum crowded with emission lines including carbon and oxygen and neon, and unusually strong nitrogen as well. Taken together, the picture is not of a universe of pristine gas slowly acquiring its first traces of chemistry. It is of galaxies that have already run through several generations of stars, complete with births and deaths and mixing, in a span shorter than the time since the dinosaurs died. Whatever process is filling the bright end of the luminosity function is also enriching the gas at a furious rate. The 2 facts point the same way. Star formation in the first 300 million years was fast, violent and efficient, and then, scattered through the same images sitting in the same fields, there is a population of objects that does not fit the story of stars at all. They were noticed almost immediately, and nobody knew what they were. In the early Sears images, and then in every deep field Webb produced, there appeared small numbers of sources that were red, extremely compact and unresolved. No structure, no extent. A point of light, of the exact shape Webb's mirror produces for anything smaller than its resolution limit. Astronomers began calling them little red dots, which was meant as shorthand and stuck. Their spectra, once taken, were unlike anything in the catalogues. A little red dot is faint and blue at the shortest wavelengths, and then, past a certain point, it turns and rises steeply into the red. Plotted, the shape resembles the letter V lying on its side. Neither half is strange on its own. Together they are difficult because a dusty object should be red everywhere, and a dust-free object should be blue everywhere. Most of them, when observed with NEA spec, show broad emission lines of hydrogen. Broad, in this context, has a precise meaning. The line is smeared across a range of wavelengths corresponding to gas moving at 1 or 2,000 kilometers per second. Nothing in a galaxy moves that fast except material orbiting close to a black hole, so they contain accreting black holes. That much is agreed. Almost everything else about them is not. Dale Kocevski at Colby College, Jorrit Matthey then at the Swiss Federal Institute of Technology in Zurich, and Ivo Labbé's group each catalogued them independently. The counts came back astonishing. Little red dots appear to be roughly 100 times more common, per unit volume, than the luminous quasars known at similar redshifts from ground-based surveys. They peak in abundance somewhere around a redshift of 6 or 7, and they thin out sharply below a redshift of 4, which is to say they are a phenomenon of the early universe that later ceased. Then came the contradictions. Quasars are strong X-ray sources. Material spiraling into a black hole heats to millions of degrees and radiates in X-rays. Chandra has stared at the deep fields for the equivalent of months. Stack the X-ray images at the positions of hundreds of little red dots, and the signal is nearly absent. They are, for their inferred black hole masses, remarkably X-ray quiet. Quasars are also hot dust factories. The infalling material warms the surrounding dust, which glows in the mid-infrared. MIRI observations of little red dots find far less of that glow than expected, and their variability is muted. Feeding black holes flicker in brightness on timescales of months to years. Repeated observations of little red dots show them holding remarkably steady. An object with the broad lines of a black hole, without the X-rays of a black hole, without the hot dust of a black hole, and without the variability of a black hole. If their black hole masses are taken at face value, the numbers are worse still. Some little red dots appear to hold black holes containing 10% or more of the total mass of their host galaxies. In the nearby universe, that ratio is about 1 part in 1,000. That ratio, and the ordinary galaxies where it can be checked, is the next thread. It begins with the black hole Roberto Maiolino found sitting inside GN-z11. Weighing a black hole you cannot resolve depends on a single elegant idea. Gas near a black hole orbits fast, and the closer it orbits, the faster it goes. Radiation from the hot accretion disk illuminates a cloud of that gas, which absorbs the light and re-emits it in the lines of hydrogen and helium. Some of that gas is coming toward us, and some is going away, so its lines are blue-shifted and red-shifted respectively, smeared into a single broad feature. Measure the width of the feature and you have a velocity. Estimate how far the gas sits from the centre, which can be inferred from the brightness of the disk, and you have an orbit. Velocity and radius together give a mass, by the same arithmetic that yields the mass of the Sun from the Earth's year. The method is calibrated against nearby galaxies, where the timing between disk flickers and line responses reveals the radius directly. Applied at high redshift, it carries uncertainties of a factor of a few. It is the only tool available. Maiolino's team applied it to GN-z11 in 2024 and found broad hydrogen lines. The mass came out near 1.5 to 2 million times the Sun. The host galaxy is small, a few hundred light-years across, with perhaps 100 million to 1 billion solar masses of stars depending on which assumptions are made. So the black hole holds a fraction of its host stellar mass that is somewhere between 10 and 100 times the ratio seen in galaxies today. Meanwhile, in the Sears field, Rebecca Larson, then at the University of Texas, examined an object catalogued as Sears 1019 at a redshift of 8.7. It too showed broad hydrogen. Its black hole weighs about 9 million solar masses. For scale, the black hole at the centre of the Milky Way, Sagittarius A star, weighs about 4 million solar masses. It has had 13.6 billion years to reach that figure. Sears 1019 had 570 million years and holds twice as much. The measurements arrived in a steady sequence after that. Broad lines at redshift 7, at redshift 8, at redshift 10, black holes of 1 million, of 10 million, of 100 million solar masses in galaxies that had barely finished assembling, set the problem out plainly. A black hole grows by swallowing matter. the rate at which it can swallow is not unlimited, because in falling material heats up and radiates, and the radiation pushes outward on the material still trying to fall in. When the outward push balances the inward pull of gravity, accretion chokes itself. That balance point is called the Eddington limit, after Arthur Eddington, who worked it out for stars in the 1920s. A black hole accreting at the Eddington limit continuously grows exponentially, doubling its mass roughly every 45 million years. Start with a black hole of 100 solar masses at an age of 200 million years. Let it accrete at the absolute limit, without pause, without interruption, for the next 370 million years. Count the doublings. You reach a few tens of thousands of solar masses. You do not reach 1.5 million. You do not reach 9 million. The arithmetic fails by orders of magnitude, and it fails under the most generous assumptions available. In 2023, a team led by Bogdán at the Center for Astrophysics in Cambridge, Massachusetts, combined two telescopes to look behind a lens. The lens was Abell 2744, Pandora's cluster. Webb imaged the field. The Chandra X-ray Observatory, which has been in orbit since 1999, stared at the same field for more than 2 million seconds, which is about 3.5 weeks of continuous exposure. Behind the cluster, magnified by a factor of about 4, sits a galaxy called UHZ1. Webb's photometry put it at a redshift of about 10.3, and NearSpec later confirmed a redshift of 10.1. The universe was about 470 million years old. Chandra found X-rays coming from it. Not many. A handful of photons accumulated over weeks, gravitationally magnified. But the detection was significant, and X-rays at that energy from that redshift can only be produced by matter falling into a black hole. From the X-ray brightness, and an assumption that the hole was accreting near its Eddington limit, Bogdán's team estimated the black hole mass at somewhere between about 10 million and 100 million times the Sun. Then they estimated the stellar mass of the host galaxy from Webb's images. The two numbers came out comparable, a black hole weighing roughly as much as all the stars in its galaxy combined. In the local universe, that ratio is about 1 to 1,000. Every large galaxy studied, from the Milky Way to the giant elliptical Messier 87, with its 6.5 billion solar mass hole, obeys a tight relationship between the black hole's mass and the mass of the surrounding stellar bulge. The relationship is so tight that it is assumed to reflect some coupling between the two, black hole and galaxy growing together, each regulating the other. UHZ1 obeys nothing of the sort. Priyamvada Natarajan at Yale, who had spent years developing theoretical models of how such objects might form, was a co-author on the paper. She had predicted, in work published more than a decade earlier, that a certain formation channel would produce exactly this signature. Objects with black holes as massive as their hosts. She had given them a name in advance, calling them outsized black hole galaxies. Finding one matters more than the individual measurement. It means that black holes did not, in every case, grow up alongside their galaxies. In at least some cases, the black hole was there first, or grew far faster, and the galaxy assembled around it. The caveats are real. The mass rests on assuming Eddington limited accretion, and the magnification rests on a lens model. Some subsequent analyses have questioned whether the X-ray source and the galaxy are the same object, but the conclusion it points toward has independent support from every broad-line detection at high redshift. Something started these black holes large. There are two stories about where supermassive black holes begin, and the choice between them has been argued for 30 years. The first story is the modest one. The first stars, the population 3 stars, were massive. A star of, say, 250 solar masses, above the range that detonates completely, collapses at the end of its life directly into a black hole, retaining most of its mass. Astronomers call the result a light seed. It weighs perhaps 100 solar masses, and it appears within the first 100 million years, inside the small halos where the first stars formed. Light seeds are guaranteed to exist. If the first stars formed at all, and if any of them were massive enough, Then black holes of roughly 100 solar masses were scattered through the early universe in large numbers. The problem, as the arithmetic in the previous chapter showed, is growth. A light seed accreting at the Eddington limit for the entire available time falls short of the observed masses by a factor of 100 or more. Worse, a black hole of 100 solar masses sitting in a small halo is a poor eater. The radiation it produces heats the surrounding gas and drives it away. Simulations of light seeds in realistic environments show them accreting in fits and starts, spending most of their time starved and growing far more slowly than the theoretical maximum. The second story is more dramatic and less certain. It is called direct collapse. Take a halo of gas with no metals and prevent it from forming hydrogen molecules. Molecular hydrogen is the only coolant available in metal-free gas at low temperatures, and without it the gas cannot cool below about 8,000 degrees. Warm gas does not fragment. It does not break into stars. Instead, the entire reservoir, 10,000 or 100,000 solar masses of it, funnels inward as a single body. What forms is either a supermassive star, briefly, which then collapses, or a black hole directly. Either way, the result is a heavy seed of 10,000 to 100,000 solar masses appearing in one step. Start there, and the arithmetic works. 45 million years per doubling, a few hundred million years available, and you arrive at millions or tens of millions of solar masses without difficulty. The requirement is destroying the molecular hydrogen, which takes a flood of ultraviolet radiation at particular wavelengths, called Lyman-Werner radiation. Such a flood exists only very close to an already forming galaxy. So the scenario demands a specific geometry, a pristine halo, massive enough to hold onto its warm gas, sitting near enough to a neighbour to be bathed in its ultraviolet light, but not so near that the two merge before the collapse finishes. Those conditions are rare. Estimates of how rare span many orders of magnitude, which is a polite way of saying that nobody knows. Natarajan's models of direct collapse predicted the outsized black hole galaxies. Bogdán found one. That is not proof, but it is the kind of thing that moves a field. There is a third possibility, growing in favour, which does not require heavy seeds at all. It requires only that the Eddington limit is not really a limit. Eddington's argument assumes a specific geometry. Matter falls in from all directions, radiation streams out in all directions, and the two meet head-on. Real accretion does not look like that. Matter arrives through a flattened disk spiralling inward in the equatorial plane. Radiation, having the whole sky to escape into, tends to leave along the poles, where there is nothing in the way. If the disk is thick enough and dense enough, another effect appears. Photons produced deep inside it are trapped, scattering off electron after electron, drifting outward far more slowly than the gas is falling inward. A photon that cannot escape cannot push anything. It is simply carried down the drain along with the gas. Theorists call this a slim disk, or an advection-dominated flow, and it permits accretion rates several times the Eddington value, and in extreme cases hundreds of times. Evidence exists nearby, a class of objects called ultraluminous X-ray sources, scattered through nearby galaxies, radiate far above the Eddington limit for the masses they appear to have. In several cases, the accreting object has been identified as a neutron star, which cannot be a hidden massive black hole. Those systems are eating faster than the limit says they can right now, in galaxies a few million light-years away. Allow super-Eddington accretion in the early universe, with its dense gas reservoirs and frequent mergers, and a light seed of 100 solar masses can reach 1 million in a few tens of millions of years, provided it is fed hard enough for long enough. This idea has recently collided with the little red dots in an unexpected way. In 2025, work led by Rohan Naidu and by Anna de Graaf at the Max Planck Institute for Astronomy examined an especially extreme little red dot, nicknamed the Cliff for the shape of its spectrum. It shows an enormous Balmer break, a sharp step in brightness at the wavelength where hydrogen atoms in a particular excited state stop absorbing. a Balmer break that strong should require a large mass of moderately old stars. But the object also shows the broad lines of a black hole, and no plausible stellar population produces a step of that size. The alternative proposal is that the break is produced not by stars but by an envelope of dense, warm, hydrogen gas wrapped around the black hole itself. A black hole accreting so ferociously that the infalling material forms a bloated, opaque atmosphere around it, radiating from its surface like a star. The name that is attached to the idea is a black hole star. It would explain the missing X-rays which the envelope absorbs. It would explain the missing variability, since the envelope buffers the flickering. It would explain the absurd mass ratios, because the masses were being read from an atmosphere rather than an orbit. It is a 2-year-old hypothesis about a 4-year-old class of objects, and it may not survive. What it demonstrates is that the black hole problem and the little red dot problem may be a single problem. None of this began with Webb. That should be said plainly, because the framing of the last 4 years has often implied a sudden crisis, and the crisis is older than the telescope. In 2011, a team led by Daniel Mortlock at Imperial College London reported a quasar in the UCART Infrared Deep Sky Survey, catalogued as Euless-J1120 plus 0641. Its redshift is 7.08. Its black hole weighs about 2 billion times the Sun, 2 billion solar masses, 770 million years after the beginning. 6 years later, Eduardo Bañados at the Carnegie Observatories found Euless-J1342 plus 0928 at a redshift of 7.54, 800 million solar masses, 690 million years in. Then, in 2021, Feige Wang, then at the University of Arizona, reported J0313-1806 at a redshift of 7.64. 1.6 billion solar masses. The universe was about 670 million years old. That last object is the sharpest version of the puzzle. Run the growth backward, even assuming continuous accretion at the Eddington limit from the moment the universe was 100 million years old, with no starvation, no interruption, no merger disruption. The seed required is around 10,000 solar masses. 10,000 solar masses cannot come from a dying star. It has to come from something else. These measurements were made with ground-based telescopes and with Hubble, published in Nature and in the Astrophysical Journal, and argued over in conferences for a decade. The theoretical work on direct collapse was undertaken precisely because of them. Natarajan's outsized black hole galaxies were predicted in response to them. Webb did not create the problem. Webb did 2 other things. First, it pushed the observations back another 300 million years, into an epoch where the growth time available shrinks to almost nothing, and the arithmetic tightens from difficult to impossible. Second, and more importantly, it revealed that the massive early black holes are not rare freaks. The quasars found from the ground were the brightest objects in the sky, 1 in a billion, selected precisely because they were extreme. It was always possible that they were flukes, the winners of an improbable lottery, and that typical early black holes were modest. Webb looked at ordinary galaxies and found black holes inside them too. GNZ11, Sears 1019, hundreds of little red dots. The population of early black holes appears to be broad, not a handful of exceptions. A single freak can be explained away. A population must be explained. And that distinction between a rare exception and a common state of affairs is exactly the distinction that determines whether the theoretical framework needs adjusting or replacing. So it is worth asking carefully what that framework actually predicted and where in it the failure lies. The framework has layers, and they are not equally certain. Confusing the layers is the source of nearly every overstatement made about Webb. The bottom layer is cosmology, the expansion history, the proportions of dark matter and dark energy, the age of the universe. It is constrained by the microwave background, by the pattern of galaxy clustering, by the abundances of light elements forged in the first minutes, by gravitational lensing surveys. These constraints come from different physics at different epochs, and they agree. Nothing Webb has found touches this layer, not once. The next layer up is the growth of dark matter structure. Given the cosmology, gravity alone determines how dark matter halos form and merge. This is computed with enormous simulations, tracking billions of particles under nothing but their mutual gravity, and the results are essentially exact because gravity is simple and dark matter, by assumption, does nothing else. That layer predicts how many halos of each mass exist at each moment. It is the ceiling Boylan-Kolchin computed against. When the universe breaker masses were checked, they were checked against this layer, and if they had survived, this layer would have failed. They did not survive. This layer stands. The layer above it is where everything happens. Baryonic physics, gas cooling, star formation, supernova feedback, black hole accretion, radiation, magnetic fields, turbulence, dust. None of it can be simulated from first principles at galaxy scales. A star forms in a region a fraction of a light year across, inside a galaxy tens of thousands of light years across, inside a cosmological volume of hundreds of millions. The dynamic range is impossible, so the simulations, illustrious TNG, Eagle, Fire, Thesan, insert what are called subgrid recipes. Formulas describing what a patch of gas does, calibrated against observations of galaxies at low redshift, where the observations are good. That calibration is the whole problem. The recipes encode how star formation behaves in galaxies like the ones nearby, made of gas enriched by billions of years of chemistry, threaded with dust, sitting in massive halos with deep gravitational wells. Then they are extrapolated 300 million years after the Big Bang, into halos 1,000 times smaller, with gas containing no dust and almost no metals. There was never any reason to expect the extrapolation to hold. What Webb has established with real confidence is a set of measurements. The number of ultraviolet bright galaxies at redshifts 10 through 14 is higher than the extrapolated recipes predicted, by roughly a factor of 10 at the bright end. Those galaxies contain oxygen and nitrogen. Some of them are resolved and extended. Massive black holes are common among them. What Webb has not established is that any of the bottom two layers is wrong. So the honest description of the situation is that a set of recipes, known to be uncertain, calibrated in one regime, was extended into a very different regime, and failed by about a factor of 10, which is roughly what a careful person would have predicted. That is not a broken universe. It is a missing chapter in a book everyone knew was incomplete. Still, calling it a missing chapter should not be mistaken for calling it a solved one. Consider what is actually not known. The initial mass function of the first stars is unmeasured, not poorly measured, unmeasured. It has never been observed even once at any redshift in any galaxy, and it enters every calculation of stellar mass, star formation rate, ionizing photon budget, and chemical enrichment. The escape fraction of ionizing photons from early galaxies is unmeasured and cannot be measured directly at the redshifts where it matters, because the photons that escape are destroyed en route. The seed masses of black holes are unmeasured. Both proposed mechanisms are theoretical constructs. Neither has been observed forming, and the observational tests that would distinguish them are marginal. The dust content of galaxies at redshift 14 is inferred from the slope of the ultraviolet continuum, using a reddening law borrowed from the Milky Way, which contains dust made by stars that no longer exist in the same form. The stellar masses of the earliest galaxies rest on all of the above, and the excess of bright galaxies has at least 4 viable explanations: bursty star formation, a top-heavy mass function, absent dust, and a contribution from accreting black holes. They are not exclusive. Any combination might be operating. Distinguishing them requires measurements Webb cannot make alone. There is a discipline in that list, and it is worth naming. Every one of those unknowns sits in the layer of the theory that everybody knew was soft. None sits in the layer that would require new physics. That is why the astronomers who work on this, when quoted carefully, sound less alarmed than the coverage of their work. Stephen Finkelstein said from the beginning that the models of star formation were the likely culprit. Brant Robertson has said the same. Michael Boylan-Kolchin, whose arithmetic came closest to identifying a genuine crisis, wrote the paper that showed where the ceiling was and then watched the data fall below it. They were not being cautious for the sake of caution. They were being accurate. What deserves the word extraordinary is a different thing entirely, and the data support it without qualification. 290 million years after the beginning of time, there was a galaxy 1,600 light-years across, blazing with young stars, its gas already enriched with oxygen forged inside earlier stars that had already lived and died. 280 million years in, another galaxy, compact and brilliant, carrying carbon and nitrogen and helium in its gas. 430 million years in, a black hole of 1.5 million solar masses in a galaxy a few hundred light-years wide. The universe did not warm up slowly. It did not spend 1 billion years assembling ragged clumps. It went from darkness to structured, chemically enriched black hole-bearing galaxies faster than anyone modelled. That is what Webb found. And the reason nobody can yet say precisely how it happened is that the crucial moment sits on the other side of a wall no telescope has ever seen through. The wall is the Dark Ages. Between the release of the microwave background at 380,000 years and the ignition of the first stars, somewhere past 100 million years, there is nothing to see. No sources, no light. A universe of cold, neutral hydrogen expanding in darkness. That period contains the answer. Whatever set the mass of the first stars, whatever seeded the first black holes, whatever conditions made galaxies grow so fast, all of it happened in that interval, and none of it emitted light, except in one very faint way. A hydrogen atom in its ground state has an electron and a proton, each of which behaves like a tiny magnet with a spin. Those two spins can be aligned or opposed. The aligned configuration has slightly more energy. Left alone, an atom in the aligned state will eventually flip, releasing a photon of exactly the energy difference. The energy is minuscule. The photon has a wavelength of 21 centimeters in the radio. An individual atom will wait, on average, about 10 million years before flipping. But the early universe was made of hydrogen atoms in numbers beyond counting, and across a volume of billions of light years, enough of them flip at any moment to produce a signal. That signal is the only radiation the Dark Ages emit, and it carries information. Where the gas is cooler than the background radiation, it absorbs. Where it has been heated by early stars, it emits. Map the 21 centimeter signal across the sky and across redshift, and you would see the first stars switch on, one bubble at a time, in a universe that otherwise contained nothing. The obstacles are severe. Stretched by expansion, that 21 centimeter line arrives today at wavelengths of meters, and the sky at those wavelengths is dominated by radio emission from our own galaxy, brighter than the cosmological signal by a factor of 100,000. Earth's ionosphere distorts what gets through. Television and radio broadcasts saturate the same bands. Attempts are underway. LOFAR in the Netherlands, the Murchison Wide Field Array, and the Square Kilometre Array in Western Australia, HERA in the Karoo Desert of South Africa, all chasing statistical detections rather than images. In 2018, an experiment called EDGES reported a global absorption signal from around a redshift of 17, but a later experiment, SARAS-3, failed to confirm it, and the claim remains unresolved. The cleanest proposal is to go to the far side of the Moon, which is the only surface in the inner solar system permanently shielded from Earth's radio noise. Small missions to test the idea have already flown. Meanwhile, the optical work continues. The Nancy Grace Roman Space Telescope will survey areas of sky thousands of times larger than Webb's deep fields, at similar sensitivity, and will find the rare, bright, early galaxies that a narrow field can never catch. On the ground, the extremely large telescope in Chile, with a mirror 39 meters across, will take spectra of the objects Webb can only see. There will be more records, redshift 15, perhaps 16, each one another few million years closer to the wall, and behind that wall, unlit and unobserved, the thing that made all of this happen is still waiting. Go back to the image. The good south field in Fornax, a patch of sky the size of a grain of sand at arm's length. Thousands of galaxies scattered through it, and near the middle, faint enough that your eye slides past it, a red smudge. The word in the title of this video is terrifying, and it is worth being honest about what that word can and cannot mean here. It does not mean danger. Nothing about JADES-GS-z 14-0 threatens anything. Its light has been travelling for 13.5 billion years, and the galaxy itself, carried outward by the expansion of space, now lies some 33 billion light-years away, receding faster than any signal could ever cross. Whatever it became, we will never learn. Its later light will never arrive. The relationship between that object and this planet is entirely one-directional, entirely finished, and entirely safe. It does not mean the universe is broken. The cosmology holds, the expansion history holds, the dark matter simulations hold. What bent, and bent by about a factor of 10, was a set of formulas for how gas turns into stars, written by people who knew they were extrapolating and said so. And yet something in the discovery does press on a nerve, and it is not scientific. It is the size. 1,600 light-years, resolved, measured, a shape on a detector. Not a point, not a statistical inference. A structure, extended across a distance that light itself takes 1,600 years to cross, already lit, already full of oxygen made by stars that had already died, at a moment when the universe had existed for 2% of its life. The instinct that says the early universe should have been simple is a very deep instinct, and it is wrong. We picture beginnings as small, a seed, a spark, a single cell. The story we tell about the cosmos borrowed that shape, because it is the shape of every beginning we have witnessed personally. The actual beginning was not small. 290 million years in, gravity had already gathered hundreds of millions of solar masses of gas, cooled it, collapsed it, ignited generations of stars, exploded them, mixed their ash back into the gas, and lit the result brightly enough that a telescope 1.5 million kilometers from Earth could resolve its shape 13.5 billion years later. That is not terror in any useful sense. It is the ordinary vertigo of finding that the world is larger and stranger than the model you carried around inside your head, which is a feeling every astronomer has had, repeatedly, and which is the reason many of them chose the work. Webb will keep looking. The records will fall. Somewhere in the data already collected, in fields nobody has finished analysing, there are almost certainly galaxies further back still, waiting for someone to notice that they have vanished from the blue filters, and the smudge sits there, red and quiet in a corner of an image, having been shining for a very long time before anyone existed who could be surprised by it.